In this video, we're going to look at the idea of definite integrals and how we can use them to find area of space underneath a line or a curve. And we're going to kind of do a little bit of a proof of it as well, so you can kind of get a general feeling of why we might use integration instead of just geometric methods. So what you can see here is we've got a graph of the line y equals 2x, a partial graph of the line y equals 2x. And what we're going to do is we are going to look for this shaded space between 2 and 5. So it's part of a triangle. And you know, one way that we could do this, if we were just doing it algebraically, is we could find this big triangle, the area of the big triangle, and then subtract the area of this little triangle, and we're left with the space in between. So let's start with that. So if we look at this, the height of this red triangle is 10. The base of this red triangle is 5. So we know that the area is equal to 1/2 the base times the height. So our area ends up being 25 units squared. Similarly, if we look at the purple triangle, we know we've got a height of 4 and we've got a base of 2. So the base of 2, and so the area is equal to 1/2 base times height, which is 4 units. And so that leaves us with the area of the shaded space, the green shaded space, which is what we're looking for. We got 25 units for the red triangle, minus 4 units for the purple triangle, which leaves us with 21 units for the green shaded space. So that's how we could do that. That's generally how we do it if we had just a basic triangle or square, something nice and straightforward. But in calculus, we also have this idea of definite integrals. And definite integrals are where we have a function that goes between two boundaries or two limits. We'll call them a and b. And the value of that integral from a to b is equal to the integral with b substituted in minus the integral with a substituted in. So after you actually take the integral and find the function, you substitute those two values in and you can get that. So remember, this means find the area under the curve, under f of x, from a to b, which is, b is our upper limit and a is our lower limit. So we've got a and b as shown here. That would be 2 and 5. This says two things. First, that the integral of f of x is equal to big F of x. We just change the notation. Sometimes you'll see the integral of f prime and then the just f of x, or if you have a function f of x in there, then we'll use a capital F just to distinguish that it's a different function. Second, that we know that, as I mentioned before, if we substitute the upper and lower limits into our new function that we found after integration, and we subtract those two things, we should end up with the area between a and b, underneath the curve or line between a and b. So let's look at it with, and as we can see, we should end up with 21 as we go through this process. So we're going to look at it with 2x. So the integral of 2x from 2 to 5. So using our integration rules, we're going to pull the 2 out. We're just going to kind of pause on that, and we're going to integrate x with respect to x from 2 to 5. So we've got 2 times, let's see, the integral of x. So it's 1/2 x squared, and we're going to take that from 2 to 5. Now this notation here, this is just kind of straight line with the boundary limits here. That's saying that we've taken the integral, but we haven't done any substitution yet. So when we do this, you know, we always want to make sure that we have equal values. And so our notation is very important. So if we take the integral and we just forget about this 2 and 5, we haven't actually shown an equivalent statement. So by doing this, we're actually showing that these two, the first line and the second line, are actually equal to each other. Okay, now as we start going further, we can see that this is going to simplify, and we're left with x squared from 2 to 5. All right, well, that's easy enough. We can now we're going to substitute in our b and our a into this function. So we've got 5 squared minus 2 squared. So we're going to have 25 minus 4 and we can easily see that that's 21 units squared, which is the same thing that we have over here. So it's kind of like a little bit of a proof by example. It does work for curves and for a lot of other things, especially when we start looking at the fundamental theorem of calculus and how all of this stuff ties together. But here's kind of a quick down and dirty summary of what definite integrals do for us and how they work for us. And in another video, we'll go into some of the properties of definite integrals and how to utilize that in a more algebraic method.